Good afternoon and welcome to this British Gear Association member focus session on the subject of non-involute testing. I am Mike Fish, Director of Dontyne Gears and the Co-Director of Dontyne Systems that produces software for the gear industry, as well as being a member of the board of the British Gear Association. The presentation today is not a detailed technical report on the subject, but presenting an outline on the potential benefits found in a specific non-involute gear form and the development behind it. British Gear Association has sponsored the development, and so more detailed reports will be available to the membership. First, a little bit about Dontyne. For those not yet familiar with the company, Dontyne is based near Newcastle upon Tyne in the north of England. It may seem remote to many people, but has a long history of engineering that has been relevant to the development of the modern world, going back hundreds of years. It is steeped in history, has many museums and beaches that are well worth a visit, so if you plan to visit, then stay a bit longer if you can, but bring a coat. Dontyne was originally based in Prudhoe on the Tyne Valley, is my hometown. Then we moved to Newcastle for better facilities when we were hosting lots of visitors from abroad. The design unit, familiar to most of you, having worked with the gear industry since 1971 on various customer projects, R&D and standards for good practices, and the BGA itself are also based in the city centre. Dontyne Systems and Dontyne Gears are now based at Washington Business Centre. Both companies are in the same building for improved development, but also benefiting from good terms from Sunderland City Council to relocate there, and there are industrial parks. There are a growing number of entities with interest in gears in that area, such as Nissan, the North East Automotive Alliance, which has over 200 members, and soon to be Jatco for gearbox manufacturer, with an increasing number of support companies for engineering and other services. Dontyne was formed in 2006 by Dr. David Palmer, formerly with Romax, and myself, formerly with Kissoft. We developed the Gear Production Suite, or GPS, with the aim to connect design and manufacturing activity internally or across the supply chain. The GPS was developed in modules such as Gear Design Pro, a load analysis module for LTCA, a machine center to simulate manufacture for accurate tool design and utilization, and the inspection center to communicate the correct design data to the inspection equipment. A further module called Optimal was aimed at utilizing the data to improve the analysis or the manufacturing. It has a gearbox model function, but can't replace the gearbox model software as it's not as comprehensive and as similar specialist software. It concentrates on the gear pair design and analysis and also correct manufacture. It is often this kind of detail that leads to problems in the greater structure. The continued increased use of GPS worldwide has proven that it is not an either-or choice compared to other gear software. Although the software can be used standalone, the modular nature means it can be used by different departments, whether in-house or external, and integrated to other software or equipment, such as machine tools and inspection units in the workshop, to improve the accuracy of the data flow and the efficiency during production. This was all before the convenient term of Industry 4.0 was coined, which would have explained our aims very nicely. Checking for potential error in manufacturing in parallel with the design development phase can lead to substantial savings in overall production time and resources. I would like to thank Romax Hexagon for this diagram, as it displays very well the aims of the software. Dontyne Systems was often asked to do project work, but not really set up for it. A separate company, Dontyne Gears, was formed in 2013 to work with customers on design projects or product development, and it was moved into the Washington Business Center in 2016. There are both workshops and offices in the building, so Dontyne Systems moved in too in 2021, which made it easier to work on products where software integration was needed. In the early stages of Dontyne Gears, it proved immediately problematic, both in time and cost, to find suppliers for prototype gears and test gear sets. It was felt that to do development projects, it would be best to have a facility with its own manufacturing and testing resources, if possible. One 1,300 square foot unit has been sufficient to house a CNC 5-axis machine, an inspection room with Osaka Shimizu gear checker, a CMM, and an equator, as well as some test rigs developed in-house. Additional cab-cam licenses for software to do the work have been purchased, such as SolidWorks, and the presence of other companies in and around the centre make it possible to avoid adding more machines, as machining blanks and heat treatment are conveniently available. The facility can help with collaborations up to technical readiness level, or TRL 6 to 7. It has also allowed Dontyne Gears to work on its own hardware solutions. Now we look at a particular project which is the theme of this presentation, and that is the analysis of a non-involute gear form. Several different tooth forms have been patented over the years, but they are not in widespread use. The principle is always the same, and that they reduce contact stress, allowing higher forces to be transmitted for a given material, or that because they do not have a base circle diameter limit, they can have lower tooth numbers and consequently higher ratios. Many of you, if not all, of this audience today will be aware of the pros and cons, so apologies for stating any of the obvious here. But it's always been difficult to implement these for several reasons. Non-involute geometry is not straight line generated, making the contact conditions more difficult to analyze, machine, and measure. Improvement in computing power and machine technology in the last 20 years has changed that situation. Any changes in tooling or equipment necessary have often made it cost prohibitive. More commonly, the fact is that potential benefits are lost in practice when the gears are misaligned. The results are stress raisers causing failures, as well as excessive noise and vibration. Dontyne Systems was approached in 2012 to analyze convoluted designs. The convoluted had been patented in 2002 by Professor John Colburn of the University of Alberta. He and Barry Berlinger, at the time president of ASI Drives and a former president of AGMA, had formed Genesis Partners to market the technology, but they had no LTCA software for the gear form. The benefits were consistent with the conformal shape of the teeth, where the addenda and dedenda were oppositely concave and convex, not just circular, but to a specific relationship that gave a constant stress through the mesh cycle. This gave rise to the usual potential benefits, that is, more power through the same size unit, the same power through a reduced size unit, or longer life. The design analysis they had carried out at a macro level to that point was very positive. The claims were very impressive, with a typical 20% reduction in center distance possible, but they had examples where anywhere up to 50% had been achieved. There were still no takers in the market for the technology, and that probably was due to the lack of detail they could put on those figures. Another thing was that Dontyne felt that it was necessary right from the start to emphasize the limitations to the applications possible, so it would not be a complete replacement for the involute, but could have these benefits in certain circumstances. Luckily, some of the most relevant applications certainly at that time, were applicable within these limits. Genesis Partners had already identified convoluted technology to be very beneficial to the wind turbine sector. In 2002 to 2008, it was a huge growth market. What impressed us most of all was the considerable work had already been done to show the potential benefits, and it was from a respected source. Certainly John Colburn had been required reading for Dr. Palmer and myself when doing our PhDs in the 90s, and we can thoroughly recommend John Colburn's books to anybody wanting to study gear geometry in any detail. But they had also, out of their own pocket, paid for the retrofit of an existing gearbox. They'd also, very importantly, done some economic arguments for the use of this, not just on the gears themselves, but on the cost of the whole box, transportation costs, and benefits to the implementation over a whole field of generators. They'd also produced prototypes on a profile grinding machine only, and some inspection reports on a CMM. They had also completed successful testing programs at Ohio State University, close to the Pennsylvania base from Barney Berlinger, but also independently at the National Renewable Energy Lab in America. As part of the promotional material that was being prepared by Genesis partners at the time, we looked at two stages of a wind turbine commonly in use at the time, though probably very low power compared to the modern size gearboxes. As you can see by the column in the middle here, the optimized involute was looked at first. That is to say, some of the parameters were adjusted to get the maximum out of the design that we could before we looked at the convoluted option. This was to avoid any conflict in the future on debate whether they actually could get more out of the existing design. So we were always looking to the optimized involute. And you can see that there are the 33% benefit on the torque now compared to the involute design. If we look at the high pass gear set, we can see that there's an even better increase, and we get 46% benefit compared to the optimized involute design. I think it was appreciated by Genesis partners straight away that Dontyne system software could save considerable time and cost on what had been up until now an empirical development process. The GPS had many of the analysis options necessary in what it regarded as the standard level option. The basis of the advanced level was the Gates program developed by the design unit. Although this was an FE package and potentially more powerful, the problem in using it was that it was hard-coded to involute designs and not easy to change or validate again. So the standard level was chosen. It had a simpler thin slice model and was easier to adapt and validate. Some new functionality was added for more comprehensive analysis. The axial resultant was added at the request of a potential customer that had experienced axial vibration in testing some non-involute designs previously. Microgeometry could already be added to tips and roots, of course, but now also to the transition zone in the middle of the convoluted tooth to avoid micro-pitting, the effects of which had already been noted in testing. A 2D FE calculation was developed in-house to avoid requiring extra third-party software licenses at this stage. This allowed the analysis and optimization of tooth roots. It also ran in very few seconds, accelerating the analysis, and has been proven very popular even for involute design analysis. The software package at this stage was then called the generic option. It was actually suitable to analyze any cylindrical tooth form and compare it like with the involute design. Several customers already had their own non-involute design they wanted to try, and by just importing the 2D profiles of the tooth, Dontyne did not need to know what the fundamentals of the form were or whether patented or not. A call went out to customers to provide potential candidates for designs, and 15 designs were forthcoming. Some designs were dismissed straight away as not applicable or not beneficial to at least 10% gain in power density. Smaller designs were actually favoured, mainly because it was considered that these were easier to bench test. However, wind turbine projects were also considered with the idea that bench testing could be carried out by Dontyne and its partners before ramping up to the industrial sizes. Reports were prepared comparing the original involute and the non-involute. An analysis of the involute design was always carried out in the new software regardless of existing analysis to establish control values and for better like-for-like comparisons. The involute designs, as mentioned earlier, were optimized where possible to ensure that the comparison to the best was made to the best possible result. Apart from wind turbine applications, electric vehicle gearboxes, especially the designs at the time, were consistently shown to be beneficial. The 3-to-1 ratios were in the sweet spot of the design technology. Many customers wanted options for reduced size and more power. The example shown here is not actually a customer example, but shows how the application of convoluted could reduce a two-stage EV drive, with grey being the involute and the green being the convoluted. It is appreciated that there may well be other limits that appear during the design project that prevent full benefits from being reached, but the potential gains here, as you can see, leave a lot of room to compromise and still have considerable benefits. In doing comparisons side by side, it becomes obvious where differences are, what could be improved, and what is not so different. The contact stress in the involute example shown here increases greatly towards the base diameter. The convoluted design is considerably less, but still has a peak around the transition zone in the center of the tooth, which could be improved. The efficiency does not differ greatly overall. Peaks in contact stress around the transition zone in the middle of a convoluted tooth can be reduced by applying microgeometry. In this example, a reduction of 15% has been achieved. A reduction in micropitting was experienced by Genesis partners in their test program after applying such microgeometry in the transition zone. It's also critical to check the conditions at the maximum and minimum center distances, which are the most common failure of the non-involute examples. For an existing application, the non-involute is compared to the involute at the established maximum minimum limits. In the case of convolute, for the example sent to Dontyne from customers, there has always still been an advantage for the given range, even in a final drive application. For new applications, the technique was to increase the maximum minimum center distances until the non-involute stress was at the same value as the involute and compare the ranges on the anticipated tolerance in the application. This slide shows a typical analysis of bending stress for an involute and non-involute tooth. The load is applied at the highest point of single tooth contact, but can be otherwise defined. Various stress parameters such as von Mises can also be selected. The optimized tooth form can be exported for independent analysis in a different 3D package. Let's look now and consider an example that was actually taken into testing by a client. This was actually for improving a final drive. As we see from the table, several examples were considered compared to the involute. They were of increasing benefit depending on actually how the parameters could be changed. The more that could be changed, the more beneficial it was, but the more risky it was in consideration to factors such as potential noise compared to the involute example. One of the striking factors is that actually in the customer's choice, their choice was actually based on a more economic or practical consideration, and in the end, the alternative 3 shown at the end, even though it was considered relatively speaking less of an improvement, it was considered more beneficial for testing purposes and implementation purposes quickly because it was the same tooth ratio as there was already in place. From 2015, funding was sought to build a test rig for validating gears of higher ratio designs. By 2018, we'd still not had any luck. Test rigs were available, but not suited to the higher ratios we were expecting to test, and new rigs proposed were too expensive and would take too long to develop. Dontyne commissioned the construction of a new back-to-back rig, recirculating power, with a local engineering company. The specification seems now very restricted compared to the current generation, but it still allows us to compare like for like. It was decided that the test gears would not be case hardened to reduce the testing time and the cost. This would still be a useful test for comparison as long as all other factors in the manufacture remain constant for the control gears and the test gears. Although no funding was forthcoming from the client, Dontyne had permission to press on with testing program. The profile grinding simulation had been used to date to define convolute gear forms, but it was felt the hub and continuous grind simulation had to be adapted to check rollout. This was necessary to prove it was possible to mass produce this form, as the customer would require them in very large numbers. Due to limited funds, 2 sets of involute control gears, 2 sets of convolute gears, and 2 sets of involute slave gears were requested. The roughing was carried out locally, but these gears were very kindly finished by Reisauer AG in Switzerland, including providing inspection reports. The results of the testing were really quite striking. The Involute was designed to fail on 1 million cycles and did so with pitting appearing. It's not surprising really that this behaviour is well understood. The first test gear set continued on through 3 million cycles. To try and accelerate the failure, the torque was increased to 25% overload, but even after a further 1 million cycles there was still no significant marking on the surface. These results were from 2021 and were put to the British Gear Association. The BGA has then sponsored a further set of testing in 2023 and 24 to see where the endurance limit actually was, and there have been even more dramatic results. More detailed full reports will be available through the BGA to the membership. The convolute principle can be applied to planetary sets in automotive and aerospace. Dontyne has carried out analysis of several planetary designs. Even though there is not a significant benefit in the ring contact, there is still an average of about 20% benefit on the power density in the system overall. The slide here shows an in-house exercise from one of our engineers who took a gear set from a car and modelled the involute and a convolute equivalent and then printed the models. Again, with 20% reduction on centre distance and 30% or more on weight, there is enough benefit to consider this option, even if compromises have to be made. Dontyne has not yet entered into a project where the manufacture of ring gears is necessary, but the GPS software can be adapted as it already has several elements in the machine center which produce internal gears, such as for profile grinding, shaping, or power skiving, and could be adapted to non-involute forms if required. In summary then, we have improved the design analysis software to check the limits of the non-involute gear forms and calculate suitable tooling. The convolute form seems to have real resilience to center distance change within production tolerances. I think it merits further study as to why. It is possible to produce such gears on existing machine tools and inspection, very important part if it wants to be ramped up into a manufacture. The initial durability tests we've seen show considerable benefits, much better than predicted really. A more substantial R&D program should be undertaken to design and test an actual convolute gearbox from scratch, and that suggests that a new project with a new design rather than a retrofit should be produced. The other thing is that the optimum design parameters seem very suited to EV and wind turbine applications, but they're by no means the only options, and it certainly warrants further investigation. These are very much at the forefront of a lot of development today. Thank you for listening. I'm sorry if the presentation was a little bit brief and perhaps a little bit superficial for some, but this very much represents the start of the investigation process. I'm looking forward to entering into more projects. I would encourage the BGA members to get involved with the activities and the standards, and I would like now to take some questions on this subject.